vector space does the coordinates of x with respect to beta live? Rn, yeah. That's just a vector of n weights or n scalars, right? So that lives in Rn. Good. And x goes to the coordinates of x with respect to the basis beta. That's called a coordinate mapping. And true or false, P sub beta is the matrix such that P sub beta times the coordinates of x gives you x, and it's called the change of coordinate matrix. True. I was going to ask you to fill in the name of the change of coordinate matrix, but then I couldn't remember it. I had to look it up, so I was like, we'll make it easier. Okay, so I found this reading and section particularly difficult. I don't know if you guys did. So in sort of the big picture, Todd, you ready? The big picture of section 4.4 is that specifying a basis for a vector space allows us to impose a coordinate system, right? And by taking any vector from a vector space and saying it's equivalent to a vector that lives in Rn, we can treat every vector space just like Rn, which makes our lives a lot easier, right? Because whenever I ask you a question about, say, P2, the set of all polynomials of degree less than or equal to 2, now you can say, well, that is just equivalent to R3, and you don't even have to think about P2. So we'll talk about why they're equivalent in a minute. Okay, so we have this thing called the unique representation theorem. It says that if you have a basis for a vector space V, then any vector in that vector space can be written as uniquely as a linear combination of the vectors in the basis. So we know that it can be written as a linear combination of the vectors in the basis because the basis spans Rn. That's the definition of spanning the vector space, that any vector space can be built from those vectors in the basis. And we know it's unique because the vectors in the basis are linearly independent. Okay, so we get this unique way to take any vector and write it as a linear combination of the basis vectors. And we call the weights that we use, C1 to Cn, those are a unique set of weights. We call those weights the coordinates of x relative to the basis beta. Okay? We give them their own, and put them in their own n-entry vector, and we call them the coordinates. Okay, so the notation used to describe the beta coordinates of x is this crazy, like, x in square brackets with a sub beta, and it just represents the column vector that is the weights that you used to build x from the basis beta. We call the mapping x goes to the coordinates of x, the coordinate mapping, determined by beta. P sub beta is called the change of coordinate matrix. Its columns are just the vectors in the basis beta, so it's not a hard thing to build this matrix. Just take the basis vectors, put them in a matrix, and you have the change of coordinate matrix. If you multiply the coordinates by the change of coordinate matrix, you get the original x back from the original vector space where it lived. And if you multiply x by the inverse of the change of coordinate matrix, you get the coordinates. All right, an isomorphism is a special kind of transformation, which is just a name for a function or a mapping. It's one-to-one linear transformation that maps a vector space V onto a vector space W. One-to-one onto a linear transformation. It's called an isomorphism. And the mapping x to the coordinates of x is an isomorphism. There's a proof in the text. You have to prove it's one-to-one, prove it's onto, and you have to prove it's linear. And linear, do you guys remember linear? It said that t of u plus v has to equal t of u plus t of v. This was from a long time ago. And t of c times u has to equal c times t of u. That was the definition of a linear transformation. So when there's an isomorphism between one vector space and another, that means that we I lost the word. hold on to, right, the same linearity. Okay. So it means that the vector spaces V and W are isomorphic if there's an isomorphism from V to W. Preserve, that was the word I was trying to think of. We preserve the linearity when you go from V to W. Okay, so whenever two vector spaces have this function, any function that maps linearly one-to-one and onto, we call it an isomorphic function, and those two vector spaces are isomorphic to each other. And isomorphic vector spaces may look very different from each other, but they act essentially exactly the same way. Okay. Any real vector space that has a basis of n vectors is isomorphic to Rn. That's sort of the big picture here. So for example, P3 is isomorphic to R4, because think about typical things in P3, right? A typical element of P3 would be A0 plus A1x plus A2x squared plus A3x cubed. That's some element of P3, right? And if I were to take two elements of P3 and add them together, you'd add the like terms, right? Like I'd add the constant terms, I'd add the linear terms. And so my A knots and my, say, B knot of another function would get added together. But if I look at a typical element from R4, it would look like A naught, A1, A2, A3. And when I add elements together from R4, you add coordinate-wise, right? So I'd add the first entries together, the A naughts. I'd add the A1s, I'd add the A2s. So the way you add in P3 and R4 is like exactly the same. You end up adding the same things. So we call these things isomorphic. Oh, no, sorry, just R4. All right, so we're going to try to work with all this vocabulary and notation. I think once we do a few examples, you're going to be like, oh, it's not as bad as it seems. It's just the notation was really overwhelming. Sure. Yeah. All right, so if we consider two different bases for R2, one will be the standard basis, 1, 0, and 0, 1. How do we know that that's a basis for R2? Standard matrix for R2. I think you're the identity matrix. Yeah, these are the columns of the identity matrix in R2. Yeah, yeah, and we know it's so that's sort of how I defined the standard basis, or one way to come up with it. But the way we know it's a basis is we have to say, do those two vectors span R2? Yeah, I can create any vector from them. Are they linearly independent? Yeah, so they're a basis. Okay, so we're going to look at the standard basis, and an alternative basis, we're going to call it gamma, 1, 0, 1, 2. Do those two vectors span R2? Yep. And are they linearly independent? Yes, because one's not a multiple of the other. Okay. So any vector in R2 can be written as a unique linear combination of the vectors in a basis. That was the unique representation theorem. So let's look at a vector 7, 4, random vector in R2. If I use the standard basis, then to build 7, 4 from the basis vectors, I would have to multiply 1, 0 by 7 and 0, 1 by 4, right? So my coordinates of x are 7, 4. Those are the weights that I put on the basis to build the vector from the basis vectors. Okay, so under the coordinate mapping determined by the standard basis, 7, 4 goes to 7, 4. Easy. All right, but if I use an alternative basis, say 1, 0, and 1, 2, how do I build 7, 4 as a linear combination of those two vectors?
3 times the second. 2 times the second, 5 times the first.
5 times the first, 2 times the second. Yeah. When the vectors get bigger, it's harder to do that in your head, and you can use we have lots of tools to help us do that, but for now we can do it in our head. So you multiply the first vector of the basis times 5, add the second vector of the basis times 2. That's going to give me my 7, 4. So we say the coordinates of x, the coordinates of this vector 7, 4, is 5, 2, the weights that we put on the basis vectors. So under the coordinate mapping determined by this alternative basis gamma, 7, 4 gets mapped to 5, 2. Oh yeah, I just made that up. Could be anything. I could give you anything. Right, no. All right, so let's look at what the heck why would we do this, right? So the whole idea of coordinates, when we're in R2, the coordinates are how you plot a point, right? So if I wanted to plot the point 7, 4, the coordinates in the standard basis mean go 7 units in the 1, 0 direction. So I start at the origin. This is my 1, 0 direction. This is my 0, 1 direction. Those are my basis vectors that I've plotted there. So the coordinates 7, 4 mean go 7 units in the direction of 1, 0, and then 4 units in the direction of 0, 1, and you land at the point 7, 4. But I could get to that same point using the coordinates 5, 2, but different basis vectors. So if I use this alternative basis to arrive at point x, I had 5 units in the 1, 0 direction, 5 units this way, and then 2 units in the 1, 2 direction. Right, so I plotted the 1, 2 direction here, so I'm 2 units parallel to that 1, 2 direction, and I land at 5, 2, which is the exact same point I landed on before. We just called it 7, 4 before, and now it's called 5, 2. Different way of getting to the same point. All right, I'm giving you that this is a basis for R3. You don't have to check it. It spans R3, and those vectors are linearly independent. It's a basis. All right, so if I want to find, I'm giving you that the coordinates of some x vector are 1, 0, 4. I want you to find the vector x. So go back to what the coordinates mean, right? Those are weights. Yeah, those are weights, and what do you put them on? On the basis vectors. So x is just 1 times -2, -5, 7, plus 0, 1, -4, 4, plus 4, -1, -2, -1. Yeah, so you get a -6, -13, 3. So that was my original x. Okay. The coordinates of this x with respect to the basis beta are 1, 0, 4. To find the change of coordinate matrix from beta, sorry, I kind of went back and forth between using b's and betas. The change of coordinate matrix from beta to the standard basis is just the columns of the basis. Right? So this is a super easy question to answer. Change of coordinate matrix is just the columns are the vectors of the basis. Oops. Okay, so now I'm giving you an x, and I want you to find the coordinate vector. Right, so what does that mean? What am I asking for? I want to, yeah, it's a point in R3 made up of the weights that I put on the basis vectors to get 5, 2, 9. Right. So I'm saying, what are my weights? We'll call them C1. C1 times -2, -5, 7. So I'm putting some unknown weights on the vectors of the basis. To get 5, 2, 9. Yeah, because as a matrix equation, right, if I was going to write this as a matrix equation, yeah, sorry. If I were to write this as a matrix equation, I would have -2, -5, 7, 1, -4, 4, -1, -2, -1, times my vector of unknowns, 5, 2, 9. And I could either take that change of coordinate matrix, augment it with 5, 2, 9, and row reduce, right? Or I could multiply both sides of that equation by what? The inverse of that matrix. So that's actually what I asked you to do in part D. So in this one, we'll just row reduce. Okay, so row reduce the augmented matrix, and we get that the coordinate matrix, the coordinate vector with respect to the basis beta is going to be 0, 4/3, -11/3. So I'll write it down. That's what the x sub beta equals. It's just a vector with the weights that you put on the basis to build the vector x. Oh. This is the notation that I use to represent the weights that you put on the basis vectors to build the vector x. Yep, you got it, yeah. C1 is 0, C2 is 4/3, C3 is -11/3. All right, so I can solve the same problem by using an inverse matrix. If I have P sub beta, right, the change of coordinate matrix, it's easy enough to get its inverse, and we could solve using the inverse. So x sub beta is equal to the inverse, I'll just write it out because we didn't name it anything, of the change of coordinate matrix times 5, 2, 9. Because if you start with the matrix equation, it's written up here. If I want to solve this thing for C1, C2, C3, I would multiply both sides of this equation on the left by the inverse of the change of coordinate matrix. So those two would, on the left, these guys would cancel and be the identity, and I'd have C1, C2, 3 by itself. And then on the right side of the equation, I'd have the inverse times 5, 2, 9. Okay, so this is called the change of coordinate matrix. It takes you from x beta back to x. If you multiply by an x beta, it'll give you the x. So in part A here, that's essentially what I did, right? Because taking this matrix and multiplying by 1, 0, 4 is the same thing as what I did here, written as a vector equation, right? So if you take the change of coordinate matrix and multiply by an x beta, it will give you the x. So see, if I take the first row of P sub beta, -2, 1, -1, multiply by this column, I get the 1 times the -2, 0 times the 1, 4 times the -1. These two things are equivalent. So the change of coordinate matrix takes x betas and sends them back to x's. That equals x, which is the standard basis, which is the coordinates in terms of the standard basis. Did you get an inverse matrix for this? Oh, okay. Mine's ready to go. So, matrix, RREF, matrix A. Change that to fractions. Okay, so I have my inverse matrix is -4/17, 19/51, -8/51, 1/17, -3/17, -5/17. 2/17, -1/51, -13/51. Multiply that by 529, and you will get the coordinates of x with respect to the new basis. Oh, nice. Yeah. Let's do that, because then I'll have it in the calculator and I won't have to. Yeah, so we'll do 3 by 3. I won't augment it, and so then I'm just going to do matrix A. Oh, okay. Oh, just do that. Right, okay. There we go. Yeah. Just to the -1, yeah. Yep. That's pretty great. All right, so now I want to multiply that matrix by the vector 529. So I'll just go into my matrix menu and put in a vector for B. That's 3 by 1, 5, 2, 9. And I'm going to take my previous answer times matrix, matrix B. And I get 0, 0, 4/3, -11/3. So exactly what we got when we did the row reducing. All right, consider P3. This is the set of all polynomials of degree 3 or less. So the standard basis for P3 is 1, t squared, and t cubed, right? Linear combinations of these things will form cubic polynomials of degree 3 or less. So a typical element in P3 looks like a0 plus a1t plus a2t squared plus a3t cubed. So I want to find the coordinate vector of P of t with respect to beta, with respect to the standard basis beta. It is, yeah. So those are just the weights, right? Those are the weights that you put on the basis vectors to create the element. So my weights are just a0, a1, a2, a3. I've been using betas and b's interchangeably. I'm sorry about that. I tried to go back and find all the b's and make them betas, and I missed a bunch. All right, so this tells us this means that elements of P3 are isomorphic to elements of R4. Okay, so it's isomorphic to R4. So that means that anytime you're asked a question about P3, you can sort of translate it into a question about R4, which is easy to answer based on all that we've done in studying matrices and vector spaces. And then answer the question in R4, and then that same answer should apply in P3. So that's what I'm going to have you do, starting with this group activity.